An organic molecule with the formula C5H10O gives the following proton and carbon-13 NMR spectra. Identify the molecule that best correlates with these two spectra. They're corresponding to the same molecule. So there's a lot of ways that we can approach this. I recommend starting with some of the very, very simple pieces of information that might allow you to differentiate. So I would look at things like number of signals and some obvious signs for different functional groups, right? So if I were looking at this proton NMR, I would quickly notice that there are 4 signals. So that tells me that I have 4 different types of hydrogens in the molecule. So 4 different sets of hydrogens. And a couple other things that I would notice right away is that I don't have those characteristic signals that I would see down here for a carboxylic acid, which was not one of our options anyhow, or an aldehyde. Okay, so we don't have an aldehyde. So that's pretty important information because that would eliminate B for us. Okay, and looking at the carbon-13, I'm going to do the same sort of thing. I'm going to look at the number of signals. So I see that I have 5 signals. So that tells me that I have 5 unique carbons. Right? And since there are 5 carbons in your molecule, that tells you that you don't have, they're all different. So there is no symmetry in this molecule. Nothing that's going to make any of the carbons the same as each other. Our hydrogens might still be the same as each other because hydrogens attached to the same carbon are likely part of the same signal, at least for the very simple molecules that we will be looking at. Okay, another key thing that's going to jump out at me here is this carbonyl. And we've already said that it's not an aldehyde. It's probably a ketone being this far down in the spectrum because we see ketone carbonyls are typically between 205 and 220 ppm. So you've got an idea that we've got a ketone and we don't have any symmetry. So with that, I think we can very quickly look at our answers. We've only got 2 ketones. This one here, of course, is really symmetrical, right? If you had C, you would expect 2C3 signals in the carbon and only 2 signals in the proton. And that's definitely not what we're seeing. So it looks like we are definitely dealing with A. And since we have that, let's go ahead and at least try to assign the proton signals. We actually looked at this carbon spectrum in an earlier video. So let's focus on the proton and make sure that it makes sense. So let me add in where all of our hydrogens are. So the hydrogens on each carbon atom are the same. And so we have 4 carbon atoms that have hydrogens. So that's giving rise to our 4 signals. So this is consistent. And then let's take a look at what we see. So we have 3 hydrogens here. It's next door to a carbonyl, so we would expect the chemical shift to be somewhere about 2.1 parts per million. And if you don't know those right off, you can get those from a table that tells you the expected chemical shift values. And then the other piece of information we want to look at is the splitting. So on the adjacent carbon atom, there is no hydrogens. That carbon has 4 bonds that we can already see. So no adjacent H's here. So that means we expect this signal to be a singlet. So this CH3 singlet looks a lot like this one. And so let's give some letters to these so we can assign them to our spectrum. So we want to say A, B, C, and D, and then indicate on the molecule where we have sets of hydrogens. So we just said that this signal here is matching what we expect for this methyl ketone. So these ones are the hydrogens that we labeled B. Okay, and then looking on the other side of the carbonyl, these other signals are actually just going to go moving away from that carbonyl, but we're also going to explain the splitting. Okay, so if we see here, we've got 2 hydrogens. So this signal would be for 2 hydrogens. The chemical shift is pretty close to this one. Methylenes, CH2s are always a little bit higher than CH3s that are the same. So we see it a little higher ppm value. So that makes sense. We'll say it's at about 2.3 ppm. And then finally, the splitting. There are two neighboring hydrogens. So N is equal to 2, right? And then for that splitting pattern, 2 plus 1 is 3. So that's why we are seeing this as a triplet. All right. And then if we look at the next set of hydrogens, and so they're just moving, lower chemical shift as we're moving away from that carbonyl. So that makes sense. It's two hydrogens because we have two hydrogens that are causing that signal. The chemical shift is in that alkane range. Not quite as low as the other one because it's still somewhat close to that carbonyl, but getting farther away. Let's see if we can explain the splitting. So it has two hydrogens on one adjacent carbon and 3 on the other. So for this one here, N is equal to 5. And so 5 plus 1 is 6, which explains why this is split into 6 signals, also known as a sextet. Okay. And so we've explained C. So this is, I guess I didn't label these. These are the hydrogens A. We just described these as corresponding to this one. So these are the hydrogens C, which means by default, although we will still explain it, this last signal should be D, the hydrogens D. Okay, so there are 3 of them, so we expect there to be 3 hydrogens. It's an alkane, so we expect it to be in that alkane range. So we would expect it to be less than 1 ppm or maybe close to 1. And it has 2 hydrogens on the next 4 carbon atom. So N is equal to 2. And 2 plus 1 is 3, which is why this signal is split into a triplet.